Hello students, welcome to grade 12 chemistry revision lesson on acid-base equilibrium. In our today's lesson, we will learn about acid-base concepts. At the end of this lesson, you will be able to give examples of Arrhenius acids, Brnsted-Lowry acids and Lewis acids. Give examples of Arrhenius bases, Brnsted-Lowry bases and Lewis bases. Identify the acid-base conjugate pairs from a given reaction. Define what is meant by amphiprotic species. Acid-base concepts. There are three ways or systems for defining acids and bases in current use. These are Arrhenius concept of acids and bases. The second one is Brnsted-Lowry concept of acids and bases. The third one is Lewis concept of acids and bases. Let us see each definition or system one by one. The first one is the Arrhenius concept of acids and bases. Svante Arrhenius, he was a Swedish chemist who framed or gave the first successful concepts of acids and bases. According to Svante Arrhenius, an acid is a substance that ionizes in water to produce hydrogen ion or hydronium ion. Acids produce hydronium ion in aqueous solution. Acids increase concentration of hydronium ion in water in aqueous solution. If you take the acid hydrochloric acid, HCl in aqueous solution produce hydronium ion or hydrogen ion plus Cl minus. Therefore, according to Arrhenius definition, if a substance produce H plus in aqueous solution, that substance is an Arrhenius acid. Arrhenius base is a substance that can produce hydroxide ion in aqueous solution. You can take sodium hydroxide as an example. Sodium hydroxide in aqueous solution increase concentration of hydroxide ion, produce OH minus in aqueous solution, sodium plus OH minus. Therefore, sodium hydroxide is Arrhenius base. Brnsted-Lowry concept of acids and bases. This is a more general definition of acids and bases because Arrhenius has some limitations. Arrhenius definition is limited to only aqueous solution, but there are a number of reactions that can take place in gas phase and non-aqueous solvents. Now, Brnsted-Lowry concept of acids and bases is a more general definition than Arrhenius definition. According to Brnsted concept of acids and bases, an acid is a proton donor. Acids donate proton to other substances. This is an acid, HN, donates H plus to the other substance. Example, look at this reaction. The reaction between hydrochloric acid, HCl, aqueous plus water, H2O, liquid. Now hydrochloric acid is a Brnsted-Lowry acid because it donates hydrogen to water and gives hydronium ion H3O plus Cl minus. According to Brnsted-Lowry concept, bases are proton acceptors. Therefore, acid-base reaction is a proton transfer process, a proton transfer reaction. You see, an acid donates a proton to the base and a base accepts a proton from the acid. Bases are proton acceptors. This is a base. Base plus H plus gives Hb. This base accepts proton. Strengths of conjugate acid base pairs. If an acid is strong, its conjugate base is weak. You can take hydrobromic acid as an example. Hydrobromic acid is a strong acid. If it loses a proton, what is formed? Hydronium ion or hydrogen ion H plus and Br minus. Now Br minus is the conjugate base of a strong acid, hydrobromic acid. Hydrobromic acid is a strong acid. Its conjugate base is weak. If an acid is weak, its conjugate base is strong. You can take acetic acid as an example. Acetic acid, CH3, COOH aqueous in water gives, this is a weak acid, acetate ion, CH3, COO minus plus H plus. Acetic acid is weak acid. Its conjugate base, acetate, is strong. Similarly, the stronger the base, the weaker it is conjugate acid. The weaker the base, the stronger its conjugate acid. You can take ammonia as an example. Ammonia NH3 plus water H2O liquid. Ammonia is a weak base, dissociates to a small extent and gives ammonium ion NH4 plus aqueous plus OH minus aqueous. You see, ammonia is a weak base. Its conjugate acid is strong. This is strengths of conjugate acid base pairs. Examples. Identify the acid base conjugate pairs in each of the following reactions. A. Dihydrogen phosphates plus ammonia gives monohydrogen phosphates plus ammonium ion. Dihydrogen phosphates is a Brnsted-Lowry acid because it donates a proton to ammonia. Now this is an acid. Acids are proton donors. Ammonia is a base because it accepts a proton from dihydrogen phosphate. This is a base. Hydrogen phosphates is conjugate base of the acid dihydrogen phosphates. This is conjugate base. NH4 plus is conjugate acid of the weak base ammonia. This is conjugate acid. Therefore, dihydrogen phosphates and monohydrogen phosphates are conjugate acid base pairs. Ammonia and NH4 plus are also conjugate acid base pairs. B. Carbonates plus water gives hydrogen carbonates plus OH minus. Carbonate is the base. Why? Because it accepts a proton from water. This is base. Water is an acid. It donates a proton. It gives a proton to carbonate. is acid. Hydrogen carbonate is conjugate acid of the base carbonate. Therefore, this is an acid. OH minus is conjugate base of the acid water. Therefore, carbonates and hydrogen carbonates are conjugate acid base pairs. Water and OH minus are also conjugate acid base pairs. Acetate plus water gives acetic acid plus OH minus. Acetate is the base. It accepts a proton from water. This is base. Water is an acid. It donates a proton to acetate. This is an acid. And OH minus is conjugate base of the acid water base. Now, acetates and acetic acids are conjugate acid base pairs. Water and OH minus are also conjugate acid base pairs. Number 2, write the formula of the conjugate base of hydrogen sulfide. As we said, if an acid loses a proton, the resulting substance is conjugate base of the given acid. Therefore, hydrogen sulfide H2S, when it donates or loses a proton, what is formed? H plus and hydrogen HS minus is formed. Now HS minus is the conjugate base of hydrogen sulfide. HS minus, hydrogen sulfide. Formic acid, the conjugate base of formic acid is formate ion HCOO minus. Is the conjugate base of the weak acid formic acid. NH4 plus, when this acid loses a proton, the substance formed is ammonium, NH3 and NH plus. Therefore, ammonia is the conjugate base of an acid NH4 plus. Amphiprotic species. Species which may either gain or lose a proton are known as amphiprotic species. Act as both an acid and a base. You can take this as an example. All these are amphiprotic species, have both properties of an acid and a base. Dihydrogen phosphate H2, PO4 minus can accept a proton plus H plus and form phosphoric acid H3 PO4. Dihydrogen phosphate can also lose a proton, give a proton to other substance. Dihydrogen phosphate H2 PO4 minus, when it donates a proton to other substance, the resulting compound or substance is H plus and HPO4 2 minus. You see? Therefore, H2PO4 minus acts as both an acid and a base, which is known as amphiprotic species. Hydrogen sulfate is also amphiprotic species. Can accept and donate a proton. HSO4 minus, HSO4 minus plus H plus gives sulfuric acid H2SO4. When it donates a proton to other substance, HSO4 minus, it gives H plus and sulfate ion SO4 2 minus. The same is true for ammonia, hydrogen carbonate, hydrogen sulfide, and monohydrogen phosphates. All these are amphiprotic species. Amphiprotic species are species which may either gain or lose a proton. Lewis concept of acids and bases. Students, as we said, the first successful conceptualization of acids and bases was given by Arrhenius. Arrhenius' definition has some limitation. A more general definition of acids and base was given by Brnsted-Lowry definition, Brnsted-Lowry concept. An even more general definition of acids and base was given by G.N. Lewis. According to Lewis' concept, according to Lewis' definition, an acid is a substance that can accept a pair of electrons. A base is a substance that can donate an electron to other substance. Species that accepts a pair of electron is electron deficient species. Therefore, for a substance to be a Lewis acid, it must have vacant orbitals. Categories of Lewis acids or examples of Lewis acids. The first category of Lewis acid is compounds with a central atom with an incomplete octet. Compounds having less than 8 electrons on the central atom. For example, beryllium chloride is an example of Lewis acid. Take this as an example. Beryllium chloride, BeCl2 plus 2Cl minus, 2Cl minus gives BeCl4 minus. Look, beryllium chloride is a Lewis acid because it accepts pair of electron from chloride ion and form BeCl4 minus. Now this is Lewis acid. This is Lewis base because according to Lewis definition, bases are electron pair donors. This is a base. The second category of Lewis acid is substances capable of expanding their outer octets by using empty d orbitals. PCl5 is an example of Lewis acid because it can accept pair of electron from the donor. Look, PCl5 plus Cl minus gives PCl6 minus. Now PCl5 is a Lewis acid. Lewis acid. Accept pair of electron from Cl minus. Cl minus is electron pair donor, is a base. Lewis base. The third category of Lewis acid is simple cations that have empty valence orbitals. Cations such as copper 2 plus, iron 3 plus, and Ag plus are examples of Lewis acids because they have empty orbitals, can accept pair of electrons. You can take this as an example. Ag plus ammonium 2NH3 to form Ag NH3 2 plus. Ag plus is a Lewis acid, and ammonium is a Lewis base. Donates pair of electrons to Ag plus. Therefore, Ag plus is an example of Lewis acid. The fourth category of Lewis acid is metal atoms that can form compounds like carbonyls. The best example of this is nickel. Nickel reacts with carbon monoxide to form carbonyl compound, nickel, NiCO4. Nickel is a Lewis acid. Carbon monoxide is a Lewis base, can donate pair of electron to nickel. Therefore, nickel is an example of Lewis acid. The fifth category of Lewis acid is compounds with a central atom containing multiple bonds. Examples: carbon dioxide, sulfur dioxide, and sulfur trioxide are examples of Lewis acids. Carbon dioxide plus water, H2O, to form the acid carbonic acid, H2CO3. Carbon dioxide contain a multiple bond, act as a Lewis acid. This is an acid. Water, there is a lone pair of electrons on the central atom, oxygen, can donate pair of electron to carbon dioxide. Now this is a base. Sulfur dioxide plus water gives sulfurous acid. Sulfur dioxide is the Lewis acid. Sulfur trioxide plus water gives sulfuric acid. Therefore, compounds with a central atom containing multiple bonds such as carbon dioxide, sulfur dioxide, and sulfur trioxides are examples of Lewis acids. Lewis base, they are electron pair donors, have excess electrons. Therefore, for a substance to be a Lewis base, it must have pair of electrons on the central atom. Students, let us try these questions so that you can practice what you have learned. You have 2 minutes. Good. Let us do together. Identify the Lewis acid and Lewis base in each of the following reactions. BF3 plus pH3 gives this compound, which acts as a Lewis acid. Which substance acts as a Lewis base? BF3 acts as a Lewis acid. This is a compound with a central atom less than 8 electrons, is an acid. PH3 is a Lewis base because there are lone pair of electrons on the central atom. Phosphorus can donate pair of electron to this, is a base. B, nickel plus carbon monoxide gives nickel CO4. Metal atoms that can form carbonyl compounds are examples of Lewis acids. Therefore, nickel is a Lewis acid. Carbon monoxide is a Lewis base. H plus water gives hydronium ion. H plus acts as an acid because it has a vacant orbital, can accept pair of electron from water. There is lone pair of electrons on the central atom. Water can donate pair of electron to this. Now H plus is a Lewis acid. This is a Lewis base. Students, in our today's lesson, we discussed acid-base concepts. There are 3 ways of classifying acids and bases in current use. These are Arrhenius systems of defining acids and bases, Brnsted-Lowry concept of acids and bases, and Lewis concept of acids and bases. We also learned about amphiprotic species. Amphiprotic species are species which may either gain or lose a proton. They act as both an acid and a base. This brings us to the end of our today's lesson. Until next time, goodbye.